space k space, and these are two tuples. Two tuples means two values, one is x and other is y. But in the basically Euclidean space we have k tuples. Definition of it is what? Definition of basically k space is what? For each integer, k, let Rk is the Euclidean space be the set of all ordered k tuples. Ordered k tuples. What does it mean by k tuples? So if we took one vector from Euclidean space, it will be like that: x1, x2, x3, so on, xk. It has k tuples. And we can, where x1, x2, x3, xk are the real numbers, we can, so rk is called these x1, x2, x3 are called the points, and these are basically real numbers. So this is the element of the space k space, Euclidean space. This is called the Euclidean space. Euclidean space. So in that Euclidean space, basically we have one thing more. We have actually these are called the points, and this is the element of k Euclidean space, where k is greater than 1. So if y, we take another element of that, another vector of that space, this will be y1, y2, y3, so on, yk. Basically we can also check the properties of addition, subtraction, and other properties on that space, and you can see it like that. For example, if we can add x vector plus y vector, so this will be, if we suppose our x1 and y1 is, x1 is 1 2 3 4 5 6, and next, and plus our y1 is 7 8 9 10, so on. Then we can add them. 1 plus 7 will be 8, 2 plus 8 will be 10, 3 plus 9 will be 12, 4 plus 10 will be 14, and so on. So on, this will be, you can also add them, and this vector, the resulting vector, will also be the uh, element of that Euclidean space, because that has the same elements, and that has the same properties like that, these two elements. So this satisfy the actually Collier property. This is called the Collier closed property, or Collier property, closed property. And this also satisfy the commutative property. So how can we check the commutative property? If we take the three vectors, we can check that property with that. Okay, so similarly you can check, if we take any number, scalar multiplication. If we take any scalar number, alpha is equal to 2, and x1 is equal to 2 3 4 5, then you can check that alpha x1 will be 2 into 2 3 4 5. This will be 2 to the 4, 2 3 is a 6, 2 4 is a 8, 2 5 is a 10. This will be equal to the, if we take, you can again take alpha common, and this will be equal to alpha x1, sorry, alpha x2, alpha x3, alpha x4. So alpha is multiplied, and again alpha x1 also belongs to Euclidean product vector. So this defines addition of vector as well, multiplication of vector as well. You can also find the you can also find that basically if x1 is a vector, if xi is a vector, this is x1, x2, x3 are the points of that. And you can also find the null vector, that is additive identity of that Euclidean space. You can write x naught, it's 0 0 0 0 0 0 0. If we add xi plus x naught, we will get that x1, x2, x3, so on xk plus 0 0 0 0 0 0. We will again get x1 plus x1 comma x2 comma x3, so on xk. So that is equal to x naught plus xi equal to xi, because there is no difference on, there will be no difference on xi, and xi will remain same. Similarly, you can check other properties of the, basically you can find the inner product, and if you multiply the vectors, basically inner product is used to do the multiplication of Euclidean space. For example, we define inner product like that. A definition of inner product. Let's do the definition of inner product. If we do the definition of inner product, we define inner product by formula. By what formula? It is also called scalar product because its result via scalar number. So if we multiply both Euclidean vectors x and y, we will get summation k from 1 to n xi and yi. For example, if we take any two vectors, if we take x1 is equal to xi, or x1 is equal to 2 3 4 5 6, so on, and yi equal to 5 7 8, so on, and we multiply the xi with the yi, then you know that a dot product of vector is I dot I is 1, j dot j is 1, k dot k is 1. So the 2 multiplied 5 will be 10. So it will be, sorry, it will be 10 plus 21. 3 7 the 21, 4 8 the 32, so on. You will keep adding and you will get a scalar number as a result of that. I hope you have understand the scalar product. And that is, if we can define another thing by that is called the norm. And that norm means if we multiply the same vectors, if we multiply with the norm length, the norm length is like that. It is denoted by x double mod is equal to x mod is equal to x Euclidean vector dot x Euclidean vector power 1 by 2. So this will be x I square power 1 by 2. If we multiply the same vector, then this is also called the norm. That is actually the length. So basically we say that a norm is basically the distance between 2 points. You can say that the norm is basically the distance between 2 points, and You can say, you can also find the norm like that, x minus y, or x minus y mod, that is the distance between x and y, two vectors, and that norm is the distance between two vectors, and suppose you can that norm vector is also greater than equal to 0, and it is 0, it is x norm is equal to 0 when x is equal to 0, if x is equal to 0. So if x vector, if we put, it means the norm of 0 is 0. Sorry, this means the norm of 0 is 0 because the distance from 0 is 0 also. If we move from 0 to 0, this will be 0. Similarly, if this norm also satisfy the basically the alpha scalar multiplication, alpha x norm is equal to alpha and x norm also, this is also equal, and norm also satisfy the Cauchy-Schwarz inequality, triangular inequality, these are also satisfied with it. Okay, so these are also satisfied, and you can we can prove that through that. Okay, so that is also easier from that. Norm also satisfies these properties. Okay, if you are not able to prove that, then I will prove it for you, because norm to prove the norm is very easy. Okay, let's do another important theorem.